Hello. In today's Principles of Computer Security lesson, we are going to be discussing about cryptographic hash functions. So in the previous lessons, we have discussed about cryptography, we have discussed about encryption, decryption, symmetric key cryptography, and public key cryptography. So we have discussed a number of topics there. But one of the things that encryption doesn't provide is integrity and authentication. Encryption protects and provides a secure communication channel. So that is the main, it provides secrecy. But when we think about integrity and authentication, there are a couple of other things that we want to achieve. That is, say, in a communication channel, we have someone, say Alice, sending some communication to a Bob. So if this is the communication that we have, and then one of the things that we want to ensure is like when Bob receives this message, they want to ensure it is the same as that was sent by Alice. There was no additional changes happening in the middle. So making sure who the sender is, that is making sure the source of the message is, that is what we want to make sure in terms of integrity, so that the data has not been modified by someone else, and also we want to know who the person, who the sender is, or authenticating the sender. So these are the two things that we can do with cryptographic hash functions. So making sure that, okay, this message actually came from Alice, and also this message has not been modified since. So these are the two things. So it is being received as it is. This is particularly interesting because when you think about attacks like man in the middle attack, where a party may, for example, sit in the middle, they may do the communication with both sides independently and keep on passing messages, but in the middle, they may modify what the message that is being communicated. So that is what we would want to avoid when we are communicating with in a channel that provides data integrity and source authentication. So if A sends a message, it, whether it passes through other parties or not, at the point of B, we are able to check, yes, this is the same as A sent, nothing has been changed, and it is actually being received from A and not by some middle party in between. So these are the two main tasks that we will try to achieve when we are using cryptographic hash function to achieve data integrity and source authentication. So when we talk about a hash function, it is again another mathematical function essentially, but it will have a few properties. So the first thing is, regardless of the length of the message, this hash function would provide an output that is of a fixed length. So that is, say if we have a very long message and a short message, both of them would have the same length of the hash function. So the main thing that we would get from a hash function is a fixed sized output. So it is a fixed size output. And then the other thing is, normally hash functions are assumed to be public. So there's no notion of private or secrecy here. Everybody knows the hash function, and we would use those hash function as a sort of public function. So these functions are publicly known. So there's no secrecy about these functions. And if there is a change in the original message, then we would also say if there's something changed in the original message, the hash message will also change. So the hash itself will react to any smaller or major changes, any changes in the message. The hash function or the hash out of the hash function will also change. So what we would want to achieve is, even if there is a smaller change, even if there is a single bit changed in the original message, we want the hash out of the hash function to reflect that. Even for minor changes, now we have a separate or different or new hash out of the hash function. So when we use these functions in a security applications, we would need couple of properties, these functions to satisfy couple of properties there. One is, it should not be possible for us to come up with a mapping to a specific hash. So that is, say, if we have a message and from the message we are getting a hash, it should not be possible to do the reverse and find the message from the hash to the message. Or there should not, it should be infeasible to find a data mapping to a specific hash. So it is what we identify as a one-way property. So it is only one way. We cannot do the reverse of the operation. And the other property that we would want to achieve is the nature of collision-free function. So that is, when we talk about collision-free functions, say if we have two messages, we have M1 and an M2, even if they have a slightest of differences, they should produce two different hashes. And any sort of random two different messages also should not produce the same hash, because again that would be problematic. So we want one-to-one, or rather collision-free mapping. So that is, no two messages are going to map to the same hash. So that should not happen in cryptographic hash functions. So in essence, what we would have is the internals of the hash function is not key here. We are not going to discuss too much about them. But the main thing, the overall approach that you need to understand is, regardless of the length of the message that you would have, so regardless of the length of the message that you may have, once you put it through a hash function, it would generate a fixed length hash value. So that is the main point here. Then when we talk about hash functions and how they may be used in the point of authentication, here we would have to use a combination of encryption and hashing to achieve that. Say we will start with the example where we are sending something from A to B. So the starting point, the source is A, the destination is B. So what we do in message authentication is verifying that the message was sent by the party that they claim to be. Say, for example, if B is receiving from A, we want to make sure that it is actually received from A. The sender is actually A. So the combination of hashing and encryption can be used in a number of ways. So what we can do is we will take, for example, take the message, generate a hash, and combine these two. Combine the message and the hash. So we will combine these two together and then take that, the combined hash and message, and do the encryption on that. So then the ciphertext that is being transmitted is a combination of the message and the hash. So then we can decrypt that, again based on either symmetric or public encryption. We can use encryption and decryption. Then once we decrypt it, again we are going to have both those components. We are going to have the message and also we are going to have the hash. Then what we can do is take the message and put it through the same hash function. So now we can also have another copy of the hash that we can compare there. So what we have is, we start with M here, we generate a hash there, we combine both of those, or rather hash of M, we combine both of those, encrypt and send, decrypt. At this point again we have Mn hash of M received. Then we take the received M and generate another hash there, and we compare these two to see if the things were received as they were. Sometimes we don't need to encrypt the message, because message secrecy is not the important point. So in this approach we are ensuring the secrecy is there, and also we are ensuring the integrity and authentication part is also there. But in some cases we don't need secrecy. In those situations we would only use encryption for the hash. So because if we use encryption for the hash, that can provide the authentication and also integrity, because again when we check the hash again from the message, again we can compare that and see that there. So that is another approach. The third approach that we may take is we may use the hashes but no encryption is there. So if we don't use encryption, then there is no authentication happening, because encryption is a way of authenticating, because the person who has the encryption key is the person who would encrypt. So that is the assumption that we have. So there, if we don't use encryption, then there's no authentication there. But additionally, we can use a combination of another alternative approach, where we start with the message and the hash and combined, then we do the encryption after that. So here it is slightly different approach, but again we are doing a similar thing. So these are like few different ways that we can do this, but the main thing to remember is this. So what we are trying to do is, we are trying to send messages from one entity to another. So we have A and we have B. So this is what we are trying to send messages between. So if A has a message, if that message is sent directly, B will receive, but anybody can come and look at this. if we have the message and encrypt it and send, here they can decrypt and get the message again. So that is the encryption approach. Hashing is we have the message and we take the hash of the message and then send it. Again, if we compare message and the hash of the message, what we would do is we will take the message as it is and generate the hash again and compare it with the hash that is received to see if the message was modified somewhere. But if we include an encryption approach here, we can additionally add the authentication part, because once it is been encrypted, we know it was encrypted by this particular entity, so we can verify that there. Particularly when we are using public key encryption, we can always verify that as well. So that is the basic idea behind hashes. We will discuss about digital signatures in one of the upcoming lessons, but this is the basic idea behind hashes. So the main point that we need to ensure is that the hash is actually transmitted in a secure fashion, because if we don't transmit the hash in a secure fashion, it can be susceptible to what is known as man in the middle attacks. Say, for example, Alice has a message that they need to send. They generate a hash and combine that with the data and send. But if a man in the middle intercepts that transmission, they can take out the data part from that. They can modify it to a new data and they can generate a new hash, and now they can send it across. So then now the receiver, Bob, is going to assume, okay, this data and the hash is going to match because these were regenerated here, but it is not the original one that was sent. So if we don't use a secure approach to send the hashes, we will not be able to ensure that there's no form of man in the middle attacks. Then another important application, which is similar to message authentication applications, authenticating the messages, is known as digital signatures. So the operation of digital signatures is very similar to message authentication. But in the case of digital signatures, the hash value of the message is normally encrypted using the user's private key. So what we do is, when we do digital signatures, what we do here is we take the message, we generate a hash, and then we encrypt the hash with the private key. So then what we can do is we can verify that here with the public key, because so here we are not doing encryption time, but what we are doing is called signing the message. So we can use the private key here and we can verify that with the public key there. Because like if we because these functions are reversible, so if we do the if we know someone's public key, so B would know A's public key, so they can use that at their point. So what A would do is A would use their private key and encrypt it with the private key. So B can decrypt it using the public key, which is already known, and they can verify the hash and they can compare it with the hash and do the verification there. So that is the main idea behind digital signatures and how it relates to public key and private key. In addition to this, we can also do what we can also do is, say, we can take the message. So message is from A. So A is going to now generate a hash key for that message. Now they will take the hash key and they will encrypt it with their private key. So then now this is combined as one entity. So this is now encrypted using a secure key. So this is encrypted and sent through a secure channel. So now it is passed on and it can be decrypted here. Then after decryption, what we can get back again is we can go back to the same point and we can take out the message, we can take out the hash, decrypt the hash and generate a new hash and compare these two. So in this approach, what we are doing is we are also adding the secrecy in the channel. So in the first case, what we did in the first case was we mainly wanted to achieve authentication. We were doing the signing and checking the signature to see if it was not modified, it is as it is. But then if we combine or include an encryption channel there, then we can also bring in secrecy to the channel. So in most realistic scenarios, this is the most likely way of digital signatures being used that you may come across. So another sort of common place where you would use hash functions, and at this point I'm assuming you are already aware of this approach, that is saving passwords on a password file or a password database. So if you are building a web application and you are collecting a way of usernames and passwords for letting users log into the system. So when you are collecting usernames and passwords, you never store the passwords in plain text. You normally and always store passwords in a hash file as a hashed text. So the hash of the password is what is stored. So even if that hash is revealed, if somebody gains access to that, it is not compromised. So whenever a user is inputting a password, say for example, what you may have in your system is say a set of usernames and passwords. That is what you need to collect. But when you are creating, you will save the usernames and a hash of the password. So then at the time of login, the users would send their username and password, but you would generate the hash of the password and you will compare these two to verify the password is correct. So you will never save the actual password. So that is one of the other sort of instances where you would use hash functions, that is to create one-way passwords. Then we may also use hashes in things like intrusion detection systems and virus detection. So again, instead of keeping the virus as it is in a database, we will generate a hash of the files in the system. So we will, and also then if things change, if things are modified, then we can check the hashes and see something has been modified. So again, this is another approach where we may use hash functions. So when we think about hash functions, more realistic hash functions are going to be fairly complex mathematical functions. So as always, we are not going to go into more details of those in this course because that is not the focus here. But if we think about sort of two simpler examples, what we can do is we can do like a bit by bit exclusive or XOR. So if we have a number of bits in a block, then we can do an XOR for each of the bits, and we can combine that into a hash function, or something like a 1-bit circular shift. So again, these are sort of simpler functions, but they are not useful from a security mechanism because they are very easily reversible, very easily. So they don't provide the same requirements that we expect from hash functions. So the main requirement that we have with hash functions is that the first thing, they should be able to support variable input sizes. So the input can be any size. So a long message, a short message, all of them should be supported. But the output should be of the same size. Regardless of the input size, the output size is going to be the same. Then, given the nature of the use of hash functions, we would expect them to be computed fairly easily. Both either at a hardware level or software level, we would want efficiency as an important factor because we would use a lot of these. We would check many things. We would use many times we would use hashing. So we would want those functions to be fairly efficient there. Then the other two main properties that we have discussed there is pre-image resistance or one-way property. So that is, we are not able to go back to the original message or predict the original message from a hash. So the reverse calculation is not feasible. Then another requirement that we would have is what is called weak collision resistant. So that is, it is infeasible to find sort of the same hashes for different messages. So that is, say, if we have two different messages y and x, if they are not equal, they should not produce the same hash output. Then the strong collision resistance is where it is for any pair of messages that collision resistance property would hold true. Then the other property that we would expect is what is called pseudo randomness. So that is, there is some form of randomness in the output that is being produced. So again, that is also something that we would expect from these hash functions. So when we think about attacks on hash functions from a security point of view, there are few different things that can be done. Brute force attacks is one possibility. So you take all the possible messages, you hash them, and you can map with the hash function to find out what the original text was. Say, for example, we have, let's take an example. We have a text called ABC, and when it is hashed, it becomes XYZ. So now we take all the possible messages, all the possible messages of this length, various length, and hash them until we find something that is mapping to XYZ. So then we can understand, okay, whatever the input that we gave to the hash function must be this. So that sort of an approach can be used in password attacks as well. Say, even if you store passwords as hashed values, if somebody will get access to a long list of all possible different password combinations in plain text, they can try to hash them all and identify the hashes. Then they can search through a hash table and identify what might be a password there. Then another problem could be, even though we expect collision resistance in many situations, there may be certain situations where there can be collisions in certain hash functions. So again, that is something that we will have to see, and that is where we would use different lengths of hash codes and things like that to make them more secure. So when we think about hash lengths, choosing the hash output lengths, uh, the idea is, if we have a longer hash length, it would be more secure. But given hashing is going to be an important part of our secure communications, uh, uh, even if we have a weakest link in terms of a hash function, that can compromise the overall security that we have. So the principle of weakest link. So we would want to ensure that it is as strong as the encryption and things like that that we may use. So that is why, say, if we use a hash function, something like a SHA hash function, we would choose the length of the hash output to be double that of the key length of the block cipher. Say, for example, if we are using 128 AES, we would use 256 SHA as the hash there. So if the key length is 128, the hash length would be 256. Then if we think about cryptanalytic type attacks, again, these are largely based on mathematical functions and how we can try to exploit some of the properties of some of these algorithms and trying to break into them. We again are not going to go into cryptanalysis in much more detail here, but be aware that some of those approaches are possible depending on the strength and security of the mechanism that you're using. So another sort of approach that we may sometimes come across is using block ciphers as a hash mechanism, and then we may something like DES, and we may string them along to produce a hash key. So that is also another approach that we may come across. But these may still have some certain other issues like man in the middle attacks and things like that. So the basic idea is there, but there are certain other problems. Again, we are not going to go into much detail into that. So now let's look at some of the most commonly used hash functions that you may come across. MD5 is a very common hash function that you may come across. This was developed in sort of first published in 91. But what has come about in recent years is that there have been a number of collusion attacks and so on that came about. So it is no longer considered a suitable hash functions in cryptographic applications. So it used to be the one sort of a standard in the 90s, particularly very commonly used. But later on, even in the earlier days, potential for attacks were identified, and in the 2000s, many sort of well-known demonstrated attacks were there. So it is no longer considered as a suitable uh, approach for hash as a hash function. So then we had SHA. SHA is the secure hash algorithm. So again, this is another algorithm like AES, something that was developed or designed by NIST, NIST, and NSA, and it became sort of the standard for digital signatures, and it is now the most common standard that hash function that we would come across in most cryptographic applications. And there are a number of variations of hash SHA as well, particularly with various key lengths or the hash lengths. And as we identified, depending on the key length, we may use a different set of these for our approach there. So depending on the message size, we may use these different hashes. Say we could use SHA-1, SHA-256, or any a combination of these things, or a different set of these things, depending on what we need to do or what we want to achieve. And the reason for the various versions of SHA is that even though SHA-1 is not broken, but it is sort of a technical infeasibility that it is not yet broken, but from a theoretical point of view, it is considered insecure because it can be broken using the similar approaches such as MD5, how they were compromised. SHA-2 or the variants such as SHA-512 are secure, but again they share the same structure, same mathematical structures as SHA-1. So again, they can become insecure at some point when again technical feasibility catches on. So SHA-3 is developed as an alternative there, a different approach, a new sort of hash function, not based on the previous ones, and tried to sort of address the issues with the previous hash functions. So one of the other important things that we should remember when we are using these different hash functions is that we would mainly be concerned about the speed of these algorithms, and how faster we can use these algorithms would be an important factor as well, because particularly when we are talking about using them in communications and such, that speed would become an important factor as well, in addition to the security nature of things. So the next topic that we are going to discuss in today's lesson is message authentication code, or MAC. So when we talk about message authentication particularly, this is in a way we can think about this as an application of hash functions, or the approaches that we have discussed in cryptographic hash functions. Message authentication code is there to satisfy our requirement for authenticating communications, authenticating the messages. So when we talk about these requirements, we would identify a number of key requirements. One is disclosure, that is, the message should not be released to people who don't possess the suitable cryptographic key. So that is the secrecy aspect of it. So unless they have the suitable cryptographic key, they should not be able to see that. Traffic analysis is discovery of the patterns of traffic between two parties. So even if somebody cannot identify the actual message itself, but if they can identify some connection between the nature of the traffic, and then that can give some indication what the communication could be, then again that is something to be avoided. So again, that is something known as traffic analysis, and again we want to avoid that. Then masquerading is a fraudulent party, somebody who is not supposed to be part of the communication channel is participating in the communication there. So that is masquerading. So with masquerading, what we would have is a like a creation of message by opponent or an attacker, and then that is put into the communication channel as if it is coming from the other original party. So again, this is like a man in the middle attack kind of a situation. One of the other things that can happen in that scenario is known as content modification. So one is, in masquerading they may send additional things. In content modification they may change the content, and say they may insert new things, delete new things, modify things. And in sequence modification, it is changing the order of things are being received. So that is also another issue depending on the type of communication that we have. Timing modification is either delaying certain messages or repeating certain messages. So these are also some of the things relevant to modifications, and things would also be of interest to us when we are talking about message authentication. Other two main things that we would want to achieve with message authentication is repudiation. So that is, source repudiation is, say if a message is received from an entity, that original sender should not be able to say that they didn't send the message. And on the other end, destination repudiation is, if the recipient received the message, then they should not be able to say that they did not receive the message. So these two things are mainly about ensuring the parties that are engaging in the communication are actually sending and receiving the messages, and they cannot deny that they send. Say, for example, if I send you a message, then I should not be able to say, no, I didn't send that, somebody had sent that. So there should be a cryptographic way of ensuring actually I sent the message. Similarly, if you receive the message, and then I should be able to make sure that you actually received the message. A simpler example, not exactly using message or in a way that you can see, is in sort of recent messaging applications. For example, you have cryptographic way of ensuring the recipients and senders. So when you have encrypted communication happening, then you can also make sure that a message was sent, and then it is actually, you can verify that came from the sender's device, and also when it is received by the recipient, then again it can be verified that the recipient has read the message. So these type of things you may come across in communications as well. So these are the main things that we want to achieve by using message authentication. So that is disclosure, that is, no other people are seeing the message. Traffic analysis, they are not able to monitor the communication and get other information about that. Masquerading, content modification, sequence, timing modification, these are about people participating, unauthorized people coming in between the communication and impacting on the communication. Then source repudiation and destination repudiation are about how the sender and the recipient cannot deny that they either sent the message or they received the message. So when we talk about message authentication code, the main idea of message authentication code is this. So we have a message here, then we have a function, a code generation function, but it will use the message and a secret key to generate the authentication code. Then the message authentication code is a combination of the secret key and the message. Then it will be attached to the message and sent. So the message authentication code will be sent along with the message. So now what the destination can do is they can again use the same code generation function, message authentication code generation function, and they can again generate the MAC for the same message, and they can compare that with the one that is received. So here, given that we are using a key here, only the parties who are having the key are able to use this here, use the generate the MAC, because the one of the elements that is required to generate the MAC is the key. So only parties who have the key can generate the MAC. So then that in turn will ensure that only authenticated people, only approved people are doing that thing. So message authentication keys are essentially, we can see them as hash functions. The only difference being here, the key is a part of the hashing there. So it is a key specific hashing. It is not a general hashing, but a key specific hashing that happens there. So then, given that key is something that needs to be shared, so then we need to have some approaches for sharing keys, things like key exchanges and things like that that we have discussed previously may be used here, and then we can use that key in combination with the message that is being received to verify that it is the message was received from the party that we expect it to be from. So if the message is X and the MAC is Y, so then we can use the X again and generate the Y again and compare that. So if one of these things are modified, whatever the code that we generate at the end would differ, and then with that we are able to authenticate the message. So the main thing that we achieve with message authentication is authentication, or message authentication code is authentication. So we are using the key to make sure the message is not modified in transmission. But if you want to ensure secrecy, we may also, in conjunction with a MAC, we may also use encryption there. So we may use different keys for both of these. For example, we may use a separate key for message authentication and a different key for encryption. And we can again calculate or compute message authentication keys before encryption or after encryption. Again, we have looked at some of these examples before as well, and it is generally regarded that if we calculate the MAC first and then do an overall encryption there. So the reason why we still want to use message authentication, even in addition to the encryption that we want to use, that is, sometimes we don't need encryption, we only need authentication. So in that case, we would use authentication, message authentication codes. Sometimes we would want to use authentication, beyond the time of encryption is needed. Say we may use encryption for a period of time for a communication, for example, but later when it is archived, when it is stored, we don't want to use the encryption because we want to store it unencrypted, but we still want to keep the message authentication code so we can verify things have not been modified. So one of the main things to remember is message authentication codes are not same as digital signatures, where digital signatures use the notion of private and public keys, whereas message authentications use shared keys. So we will discuss about digital signatures later, but what we are discussing today is message authentication codes that use a shared key there. So when we talk about message authentication codes, and when we talk about the potential attacks on message authentication codes, and when we assess the security of a message authentication code function, MAC function, we need to consider the type of attacks that may be targeted against that message authentication code. So based on the type of attack, we will have to see what are the requirements there. So the first requirement that we will have to think about is to do with message replacement attacks, where an opponent is able to construct a new message to match the same MAC. Say, for example, say what we have is a message, and for that message, we have a message authentication code X. So, if somebody can compute, say, a different message M1, but still producing the same message authentication code, that is a problem. So, that is what we identify as message replacement attack. So, we can replace the message, but the same message authentication code would work. So, that is a problem. So even though the opponent doesn't know the key, so they are not relying on the secret key to generate this, they try out various messages and key combinations until they come up with this message authentication code. So then they can use that. So that is something that we want to avoid. The second thing is to do with brute force attacks. So if they can choose a plain text, say for example, they can choose a plain text and they can keep on doing a brute force attack until they find the suitable code there. So that is also something that we want to avoid. Then the last one that we would want to achieve is the authentication algorithm should not be weaker when we are considering a particular message. It should treat all the parts of the message equally. So some may be equally easily guessed and some are not easily guessed. That type of thing should not be there. So again, these are some of the requirements that we would consider when we are talking about a MAC function. So one of the common approaches, or like sort of increasingly there's a common interest in using cryptographic hash functions as part of message authentication codes, or using a combination of cryptographic hash functions as part of our message authentication codes. So what we can do, what can happen here is, say something like MD5 or SHA, and then we may use something like that as part of our approach for a message authentication code. So this is what we would identify as hash message authentication codes, or HMACs. So the way that we would go about building message authentication codes with hash functions is, so what we would do is we would take the message and combine it with the key and put it as the input for the hash function. So that will generate the hash. So generate the MAC. So this is not going to be as secure as a dedicated MAC function, a different function, something like an encryption function. But what we get here is we get a more faster execution, for example. So the security of using hash MAC functions depends on the cryptographic strength of the underlying hash function, depending on the type of function, the collision freeness, and all those things of the hash function will determine whether that is a suitable approach for as a hash function. So depending on things like message replay attacks and things like that, we may identify some as more suitable than others as hash message authentication codes. Then the last thing that we want to discuss today is known as authenticated encryption. So the idea of authenticated encryption is that we simultaneously try to give confidentiality, so that is the secrecy part of it, and also the integrity part of it, the authenticity of the communication at the same time. So this is where we use this combination of authentication and encryption together as part of our message communication approaches. So this is where things like the approaches where we were looking at using hashing and encryption one after the other, or authentication and encryption, or encryption and authentication, or independently doing these things. So these are some of the approaches whereby we are achieving both of these things, confidentiality and authenticity. Because confidentiality is all about the secrecy of the communication that is happening in a communication channel, whereas authenticity is about authenticating the origin sender, for example. So when we think about these different approaches, there are various different reasons why we may go for one or the other in terms of as a suitable approach here. So we could use things like, say, hashing followed by encryption. Where we first compute a hash cryptographic hash, and then we encrypt the message and the hash together. So these are the examples that we have discussed previously as well. So alternatively, say authentication and then encryption. So here we will have to use two different keys, one for the authentication and one for the encryption. One may be a public key, one may be a shared secret. So we may use these different approaches there. So the main thing to remember here is that the main goal that we have here is we achieve both of these things. Because when we think about a communication, when we think about having a secure communication, both of these things are important for us. That is, having a communication channel that ensures confidentiality, so that is, it is secret, nobody is able to listen into that channel, the third parties are not going to able to come in and listen or modify things there. That is confidentiality part of it. And authenticity is also, these third parties cannot come and modify things, and we are not able to make sure that it is actually from the origin point or not. So these are some of the things that we will achieve from this. So that's all we have to discuss in terms of cryptographic hash functions today. We will discuss about digital signatures in one of the coming lectures. So until next time, thank you for joining.